Hi. Whoa, that's loud. So I will be talking a little bit, a lot actually into what Pietro was just talking about, because TinyML is very much also a component that can be used in this topic. So my name is Paul Schwartz. I am founder and co-founder and CEO of SenArch. And SenArch is a Danish company. It's actually a university spin-out. And in today's session, I will be talking about how we can leverage IoT technology, TinyML, and specifically our gateway, our solar-powered SenArch ARCH1 gateway in our, you could say, dealing with the effects of climate change. So, what is rapid wildfire detection, and why is early detection really important for us to deal with this destructive effect of climate change? Well, first of all, every year we face these disasters, and every year about 350 million hectares of land and property is lost to wildfire, destruction of ecosystems, destruction of life, assets and infrastructure. And in addition to that, over 105 billion tons of CO2 is released into the atmosphere. So it's actually a vicious circle when we don't try to react and prevent these wildfires from going out of control. In the event of ignition and a wildfire starts, the fire typically grows and accelerates between, it doubles every 3 to 5 minutes, which means that early detection is critical to avoid things, raging out of control, a wildfire raging out of control. Also, we spend, on a global level, we spend between 5 and 10 billion US dollars on fighting these fires once they have gone out of control. So it's obvious that if we can leverage the IoT technology that we already have and use today in actually preventing the fires from escalating or even starting in the first place, using, for instance, edge computing and AI and these kind of machine learning data models that I will come back to a little later in the presentation, we can actually predict where the risks are in a certain area and thereby actually defend ourselves from the fires even starting in the first place. So, a little bit of a presentation of our solution. We have, at SenArch, developed a solar-powered gateway, which is a LoRaWAN or a IoT gateway, where you can collect data from sensors in the environment, monitoring on different parameters, different physical parameters, such as temperature, humidity, ground soil moisture, wind speed, wind direction, things like this, and then using that data to actually, you could say, predict and use in data models to risk assess and provide the necessary resources to certain areas where the risk is highest, thereby preventing the wildfire from even happening. The gateway that we provide can thereby be a backbone for all this environmental data. And this is what our customers, some of our customers, are using the gateway for. We developed it for a lot of different applications, but in this session, I will be talking about how it can provide an environmental monitoring backbone. Using our sun as a source of power is obviously fantastic. But if you're building, like we are, a gateway that is on all the time in any kind of environment, you need to balance the energy consumption with the size of the solar production and storage solution. And what we've done is we have radically reduced the energy consumption and made it very, very efficient, so we can survive on battery alone for up to 30 days. This means that we can say that we have a very reliable system that is not depending on days like today, which obviously, is a no-brainer from a solar point of view. But we come from Denmark, where the sun is not shining for months. And so having a solution that is capable of surviving the Scandinavian winter was in fact our ultimate, that was our ultimate KPI when we started the project 2 years ago. So we provide the system with 3 different sizes of solar panels and batteries, so we can design a solution depending on where you're going to deploy it in the world. Obviously, in this area, we would provide a 50-watt solar panel and probably like a 22 amp hour battery or a 50 amp hour battery. But going north to our parts of the world, we can go up to 150 watts solar panel and 100 amp hour batteries to survive the long winter. Another key feature for wildfire detection and prevention is that it's a non-lithium battery. Obviously, lithium batteries are flammable, and that's also why when we check into the airport and enter a plane, they tell you not to charge your power bank, because a lithium battery, under the wrong circumstances, can actually ignite. And so from an ecological point of view, it doesn't make any sense to use lithium batteries for protecting against wildfires. So we use other chemistries for batteries which are not flammable, and that is actually one of the game changers for this solution. I said that we come from Denmark, so we've built, because of that, we've built a solution that is very ruggedized and very reliable, even though we have like last December, we had 17 days of no sunshine at all. So this kind of robustness, this reliability, and being able to function over the course of a year is one of the key components and the key requirements of our solution. Also, our system is modular. So all the system components, the solar panel, the battery, the gateway enclosure, the battery enclosure, all these things are disaggregated and can be installed according to the circumstances of the individual installation. You can put it on a pole, you could put it on a rooftop, on a wall, on the ground. It's a very flexible tool set. And of course, as any other gateway for IoT, it can scale as a function of how many gateways you install. So you can install one in a certain area and giving you like a bubble of connectivity, or you can do regional or even national networks for this. And then, of course, all the different functionalities of the gateway are remotely monitored and managed, and we can update software over the air, all the functions, even down to certain system components can be updated, like the charge controller for the battery and the solar panel. That we can update over the air. We can change the configuration so we can support battery chemistries that we don't even have today. So when new batteries come into the market and become affordable, you can update the charge controller in the system and thereby support this new type of battery. So why did we choose LoRaWAN as our chosen connectivity technology? Well, first of all, the radio modulation of LoRaWAN and here I'm probably preaching to the choir because you guys are used to working with these technologies. But one of the main features of LoRaWAN is its ability to have long range and penetrate, trees and bushes and buildings and other obstructions. So the radio modulation type is really beneficial for that. Another really beneficial thing about this is the ability to reduce the power consumption on the edge node on the sensor side. So again, coming back to the ability to predict and warn against wildfires, we are looking at using sensors that are energy harvesting on their own. So small sensors with no batteries, at least not lithium-based batteries, but having a small solar panel so they can be self-powered over time, thereby reducing the risk, but also having an ecologically sustainable solution and avoiding having to change batteries every 5-10 years. LoRaWAN also has some very good features when it comes to data resilience, being able to provide retransmissions and making sure that you receive the data packets that you are expecting. And that's also very beneficial. But finally, we have developed something that we call gateway relay, which means that we can use LoRaWAN as our backhaul technology as well. So using one channel in our gateway, we can so to speak daisy chain backhaul sensor data from areas that do not have any type of internet connection. So typically in an environment like this, we would use a cellular network to backhaul the data to the cloud. In a very remote, extreme remote location in the forest or in the wilderness where there's no cellular connection, where the only option is satellite, which is very expensive and energy taxing, we can backhaul the data from sensors using our relay function, and we can actually jump 8 gateways back. And if you figure that each gateway has a range of maybe 10 kilometers, that really reduces the complexity and brings the data back over a very long, long distance back to an area where we can upload the data to the cloud using cellular, for instance. So a real application, real-life case study is the FLARE project, which has started as an EU-funded application project, where we, together with the Danish Technical University in Lyngby, Denmark, working with a professor Drews, Martin Drews. He is a PhD in environmental risk assessment and management. He and his team have developed data models for actually predicting the negative effects of climate change. That can be, in this case, wildfire, but they're also working with the risk of flooding, which is a huge issue in Denmark because we're such a low and flat country. So they are able to take data from sensors, from web services, from meteorological weather data, and then chew on that data and come up with risk assessments and indicating where the high-risk areas are. And so you can actually, if you are an environmental agency, you can allocate resources to those areas before the catastrophe even happens. And the same methodology is used in the FLARE project, where the team of scientists at DTU, the Danish Technical University, are providing the data models for the predictive analysis and risk assessment of wildfire. So we provide the infrastructure for the sensors. The sensors are providing the environmental monitoring data. The data is then captured and sent via the gateway to the cloud, where the data models are then providing the very detailed assessments of the risk and indicating on a map where the high risk levels are and where the resources should be spent. And thereby, we can actually predict and prevent the ignition from happening in the first place. And as I said, this is the workflow. So the sensors capture the environmental data, forward them on to the gateway, with or without tiny ML, edge computing. But the general idea is to have sensors in nature, providing the real-time data, the gateway relaying that data back to the cloud, and the data models then providing the analytics and the alerts, which can then go to the authorities in the form of API or SMS or email service, whatever is needed to alert the appropriate resources. So, all in all, the idea here is to not invent something that we don't have. The idea is to actually leverage the technologies that we have available today, create an open technology stack with an open ecosystem, using the technologies that are standardized and open, providing a tool set for the authorities to actually risk assess and manage the threat of wildfire, and actually also being able to prevent the fires from happening, because we can say these areas are the areas where you should be allocating resources and doing, for instance, cleanup of the fuel on the ground, maybe watering down, or who knows, or doing control burns before they happen by themselves. So we believe that we can be smart about this. We can, with the resources and the technologies that we have in the ecosystem, we can provide the tools needed for this type of application. And we encourage the ecosystem to work with us to create a smarter and more sustainable future. Thank you very much.